Hi, everyone. Thank you for joining us. My name is Rosa, and I'm a senior researcher at University of Nottingham. My research focuses on developing practical solutions for decarbonizing our energy systems, particularly through ammonia and, most importantly, aqua-ammonia. We at the University of Nottingham decided to run this webinar as a part of Net Zero Week, and not only to give ammonia the attention it deserves, but also to introduce you to what we're doing and we're progressing at the University of Nottingham as the first developer of a novel concept of aqua-ammonia. We honestly believe ammonia deserves a specific attention because of its incredible characteristics as a fuel. The most important deterrent factor to widespread the ammonia as an ultimate alternative to natural gas so far is its corrosiveness and toxicity. And I'm using past tense here because thanks to the introduction of aqua-ammonia, most of challenges can be practically handled. So we have an hour and a half together. We're going along with our speakers, share some of our latest research, and discuss how ammonia and aqua-ammonia could help accelerate the transition to net zero. Within these 90 minutes, we have our wonderful speakers. We are delighted to be joined by our recognized experts from University of Cambridge. We have two speakers from University of Cambridge and another recognized expert from Cardiff University. I myself from University of Nottingham will cover the discussion on aqua-ammonia and the broader impact of ammonia, including preparation, energy storage, and combustion will be covered by the other three speakers from University of Cambridge and Cardiff University. Our first speaker is, so here's a timetable for our webinar here. Our first speaker from University of Cambridge is Professor Laura Torrente-Murciano. I give a very short biography from her before we hand it over to Laura. Professor Murciano is internationally recognized for her research in green ammonia and sustainable chemical engineering. Her work has advanced innovative technologies for producing ammonia from renewable energy. And she has been recently awarded Royal Academy of Engineering, the prestigious Green Future Fellowship. Laura, could you please kindly share your file and go ahead?
Of course. Yes, Rosa, thank you very much to you and the whole team at Nottingham for organizing this event. It's an absolute pleasure to be here and to describe a little bit what we are doing in Cambridge. So let me put this in presentation mode. So just taking advantage of being the first speaker today, I'm going to provide an introduction about this molecule that we are talking about today, ammonia. Let me start saying that this is a fundamental molecule in our society today. So we feed the population today by artificially producing this molecule in chemical reactors. So for us, most of us living in Europe, around 80% of all the nitrogen atoms in our body forming proteins and so on have been produced in chemical reactors. So fundamental a molecule. This molecule is not that different to this other one, methane. And we use methane as an energy carrier today, right? So most of our societies, again, in Europe, are built on the use of methane for electricity production, for heating, and so on. Now, the way that we make ammonia today is by using methane. So or other fossil fuels, I should say. So we take the hydrogen from these molecules, we combine it with nitrogen from the atmosphere, and we produce ammonia. And I will go into a little bit more detail later about how we do this and why it is important that we think about alternative ways. So what we are going to present today is how we are trying to make the same molecule by using exclusively renewable energy. And renewable energy, water as a hydrogen source, and nitrogen from air. But let me give you a broader picture of why we are doing this. And it's not only to decarbonize fertilizer production, it's much, much more than that. So let me start by saying, okay, this is our energy transitions today. So our society, we like it or not, is strongly dependent on the use of fossil fuels, and they are very good. They are very good because they are very flexible in the way that we can use them, so they meet most of our energy demands, if not all. So we use them for electricity, transport, mobility, heating, chemical industry, and so on. And over the last, let's say, 2 decades or so, we've seen the implementation of renewable energy into our energy systems, and that's been very good, but mainly to produce electricity as it is. And then through batteries is going into transport with electric vehicles and so on. There are 2 big elephants in this slide, as you can see, and is that this system produces a lot of CO2 emissions, but also an equally important methane emissions. And today is extremely hot in Cambridge, so I don't need to really explain the implications of that. And our vision is we can fully replace fossil fuels. Sorry, let me see if I can move the slide by using ammonia. And then that will obviously produce also green fertilizers and decarbonization of part of the chemical industry as well. But why ammonia can occupy the space of fossil fuels is because we can produce it directly from renewable energy. It will store energy. And as I say before, the methane and the ammonia molecules are not that different. So they store and they release energy in exactly the same way. But if I go a little bit more in detail about why ammonia is carbon-free energy vector, that's obvious. It has a very high energy density. It can be liquefied at very mild pressures at room temperature. It has more hydrogen in liquid ammonia that we can store in a 700 bar hydrogen cylinder because of the high energy and volumetric density. And then the other thing that is very exciting is it's very versatile. So I was saying before that fossil fuels are very good because they are very versatile. We can use them in different ways. Ammonia presents similar characteristics. So we can crack it and release hydrogen. And my group has been working on that for 15 years, how to produce efficiently hydrogen from ammonia. There is very, very exciting research about how to produce or how to use ammonia directly in fuel cells. And the thing that is exciting me a lot these days, and I'm not an expert here, so I'm looking forward to the Cardiff presentation, is the direct ammonia combustion in combustion engines. And the other thing that is important is we already have an infrastructure, a transport network for ammonia. And in this map, I'm showing how ammonia is distributed around the world with the different dots are ports where ammonia is traded, okay? And this is because of the fertilizer industry, but that means that we know how to handle ammonia, we know how to transport ammonia, we know how to store ammonia. So all that knowledge is already there. Now, how do we do it today? How do we make ammonia? What are the issues of making ammonia today? Well, we use the famous Haber-Bosch process, and this is something that is so important that we even studied in A levels, right? And it's a process, without going into loads of detail, that it consists on 2 steps. The first one is hydrogen production, where we take, as I said before, natural gas, fossil fuels, and produce hydrogen. And the second step is the ammonia synthesis loop, also called the Haber-Bosch loop. And that's where we combine hydrogen and nitrogen to produce ammonia. These 2 steps are hugely integrated. And this is a process that has been optimized for over 100 years. Loads of small innovations and new technologies means that this process is now reaching almost the thermodynamic limit. So it's fantastic, fantastic piece of engineering. But because we use fossil fuels, then this process is also responsible of around 2% of CO2 emissions. And to put that into perspective, 2% CO2 emissions is similar to the whole aviation industry. So, just for fertilizers, we should decarbonize this process. But if we can use green ammonia as a way of also storing renewable energy, then we will fully transform the society and be able to decarbonize it. So green ammonia is not that different if you think about it. It also has these two steps, but in the first one, we produce hydrogen from water splitting. Okay, and the second one, it could be exactly the same. I will explain in a few minutes why it cannot be. But the main thing is, you probably noticed that there was an arrow connecting the first step and the second one when we produce ammonia from fossil fuels, and that is energy being transferred, integration happening between these two steps. When we produce green ammonia, that whole integration and optimization breaks down. So we need new processes to be able to make green ammonia efficiently and, as a consequence, cost effective. So where are we? To produce green ammonia, this scheme shows that we will use renewable energy, electrolyzers for hydrogen production, and then the Haber-Bosch loop that I was mentioning before. Now, what we have in this cycle is, on one side, we have an intermittent source of energy. So, and that is the main problem in making green ammonia or even decarbonizing any process, as we call the power-to-X chemical processes. And then on the other side of this circle, we have green ammonia production, which runs 24/7 for years, and a constant capacity. So how do we manage this kind of imbalance? So an intermittency on one side of the equation and a constant energy demand on the other side. Well, it's as simple as putting a hydrogen buffer in the middle. So we will produce more hydrogen when we have more energy, and then we will consume it at a constant rate. The problem with that simple solution is that it makes ammonia very expensive. So we've done calculations about what will be the cost of making ammonia in the UK. An average cost is around 1,500 to 2,000 pounds per ton of ammonia. And you can see here the breakdown, which is dominated by that hydrogen buffer. Now, to put again this into context, the cost of ammonia using fossil fuels oscillates because it's strongly dependent on methane cost, but these days is around 600, 800 dollars per ton. So we cannot make green ammonia cheap enough at the moment with the technology that we have. And what we need is to balance that equation differently. So renewable energy is always going to be intermittent, no question about that. Can we produce technologies that make green ammonia production intermittent as well, flexible enough to mimic the energy profiles? And by doing that, can we reduce the cost? So I'm going to give you an overview of what we are doing on that sense. And let me start saying that this is the Haber-Bosch loop. We don't need to go into a lot of detail, but it consists of a reactor and then a separation using condensation. This is a reaction that is thermodynamically limited, which means that you cannot really go beyond 20% conversion every time that you go through the reactor. So this is, chemical engineers have this very well-known trick. You separate your product and recycle your unreacted hydrogen and nitrogen. And by going through the loop again and again and again, you finally convert all the hydrogen. But it's very rigid in the way that it works. And it's important to say that it's an exothermic reaction. So you need to be very careful with heat management. Otherwise, you can easily go into a runaway situation. Right. Then what we are doing, and this is inspired by work done at the University of Minnesota by Professor Ed Kassler, now retired, who say, okay, maybe the problem is not the reactor. Maybe the problem is at a higher level, is at a system level. What if we replace the condenser with a different way of separating ammonia, such an absorption? And by doing that, you can immediately run the process at much lower pressures. Much lower pressures means that you can start ramping the capacity, having a flexible process and a safe process as well. Now, the problem is absorption is well known in the refrigeration industry. Ammonia absorption is well known. You can separate ammonia using metal halides. They are cheap. But all the knowledge in this area is at low temperatures, is for refrigeration. What we don't know, and this is what my group is trying to understand, is how we can use it at high temperatures. What happens with absorbers? They decompose, they agglomerate. It's a completely new process, and we are developing quite a lot of science to understand all that. But we also went one step forward. We are doing quite a lot of catalysis work, and then what we thought is, if we can identify a catalyst and an absorber that work at the same conditions, say temperatures and pressure, then we can integrate the whole process into a single reactor. And that is what we've done and we have demonstrated. So in this new process, you have a single reactor, you forget about the compressors, the loop. So it's much, much simpler in terms of operation, and is particularly good for a small scale ammonia production. And why is that important? Well, for two main applications. So the first one is we can start delivering fertilizers in Africa, in remote locations with no access to infrastructure, but also renewable energy is distributed by nature. And I think that we need to start thinking about much smaller chemical processes than the ones that we have today. So if we compare where we are today with where we want to be, is we have a system, the conventional Haber-Bosch, which is designed, optimized, and integrated for fossil fuel utilization. And that is, in my opinion, a false optimization. If we want to use renewable energy, we need to think about completely new technologies, new processes, new ways of doing heat integration. And because, as I say a few times already, the intermittency of renewable energy is the main technical and economic challenge. And then this new process is also low capex, very small. So we are kind of challenging the concept of economy of scale. It is designed for intermittent operation and distributed production. As I say, we need a portfolio of technologies to make this decarbonization a reality. And focusing on this, well, probably you have realized that the single vessel process that I'm presenting here is a two-step process. It's not continuous. So in one step, you produce ammonia when the sun shines or the wind blows, but then you need to desorb it, you need to release it, and that requires energy. So if you do the energy calculations, you will see that that kills completely the process. So we have also developed a technology that is able to store heat at different scales. And for that, we also use chemical reactions. So it's not sensible heat, it is chemical heat storage. What are the implications of this? Well, what we are doing is to really understand the effect of the intermittency in decarbonizing chemical processes as this one. And we are taking the energy profiles, the historical energy profiles for loads and loads of locations around the world. And this is showing a map of around 3,000 locations in Europe. And then what we do is we optimize what will be the optimum combination of renewable energy production, electrolyzers, hydrogen buffer, and ammonia plant capacity to minimize the cost of ammonia. So we are doing this kind of algorithms to come up with this optimum design. And here is where I show again that using conventional technology, conventional approaches of designing processes, it's just not possible to make ammonia, even in places with very, very high wind capacity like in the UK. It's not possible, sorry, let me rephrase that. It's not possible to make ammonia cheaply enough. We have the technology to do it today. Now, what we are developing is this concept of when you are talking about renewable energy and considering the fact that the cost of production of renewable energy is dropping to the point that it's cheaper than fossil fuels, then utilization of renewable energy shouldn't be the way of optimizing processes. And this map shows what is the economic advantage of curtailing energy. So what I mean is not using part of that energy, at least for ammonia production. We might find uses through sector coupling in other sectors, but not for the design of the ammonia plant. And if you do that, then you can see that there are many, many other locations that start becoming interesting. But still, most of the points in this graph are still in the yellow oranges, which are completely uneconomical. But with new technology like the one that I showed today, so technologies that are able to mimic the energy profiles, then we can produce ammonia, green ammonia economically. Okay. Let me change the scale here. I mean, these three maps at the moment have the same scale, and that is in purpose, obviously, so you can see the evolution of the cost. But it's not very useful in this last map. So let me change the scale there to show where it is economically feasible. So if we do a combination of solar and wind, and then we also use these new technologies, then you can see that we certainly can produce green ammonia cheaply enough in the UK. And this is the right time to do this. It's the right time to engage with, politicians and so on, because the technology is being developed to make this a reality. So these are a few pictures. This is Mitsubishi in Japan developing combined cycle ammonia turbines and demonstrating them in Singapore. This is a picture of a tractor developed in the States to use ammonia. And then this is my group visiting shipping cargo in London a couple of years ago, coming from Singapore to London when the IMO was going to regulate the use of ammonia for shipping. So the regulation is being developed. End user technology is almost there. This is the time to produce green ammonia. So let me finish with, again, the vision. We can replace fossil fuels using green ammonia as an energy carrier and fuel. It has different uses. So for transport, fertilizers, obviously, fuel for power generation. And if we do this, then we can produce a completely new energy trade system around renewable energy, similar to the one that we have around fossil fuels today. So with that, I think that I'm on time. I just want to acknowledge my research group, which is a fantastic group of engineers, scientists, and chemists, and few other disciplines there. Everybody who is funding us, I'm very excited, as Rosa said, for this new opportunity to take these technologies to higher TRLs through the Green Future Fellowship, all the support from the Royal Academy of Engineering, and thank you very much to all of you for your attention.
Thank you very much, Laura, for your fantastic talk. That was wonderful. The technology, the how you presented the technology, that was perfect. Thank you so much. So, is there any question for Laura? We have 2 minutes here for answering the questions. I'm just looking through the chats, and we have two comments here, not any question. Is there any question?
Can I ask a question?
Yes, sure. Go ahead.
I'm just interested on the commercial side of things. What are you doing to raise funds for this new technology, and do you need help?
Okay. Well, we are always looking for funds. I think that's the role of an academic these days. So we just got this 10 years fellowship program from the Royal Academy of Engineering to develop some of these technologies to higher TRLs. And some of the ones that is so today are at TRL 3-4. We want to go to 6-7 to be able to take it forward. You know, the faster that we do, the higher the impact it will have. So happy to, you know, continue the conversation and just explain more what we are doing and how we are doing it.
How do we get in contact with you?
I can give you my email address in the chat.
Okay, thank you very much.
It's on online, but I'll put it on the chat.
Thank you very much indeed.
No worries.
Thank you.
Thank you. It was quite helpful. Thank you so much. So it is 9:30. We are getting ready for our next talk. We had preparation of ammonia, green ammonia preparation. After that, we have to think about how we store this ammonia. And this is a question that Alex from University of Cambridge is going to cover and answer it. Dr. Alex White is a senior researcher in thermofluids at University of Cambridge and a fellow of Peterhouse. His research focuses on thermodynamics, energy storage, heat pumps, and advanced power generation system. He has made significant contribution to the development of large-scale energy storage technologies, and more recently, to the use of ammonia as a zero-carbon energy carrier for future energy systems. I hand it over here to Alex, and I hope you find it useful. Thank you, Alex.
Thank you. Thank you very much, Rosa, and thank you very much for the invitation to speak at this webinar. I think I'm going to give a slightly different perspective on the use of ammonia here. Laura has talked a lot about the issues of intermittency of renewable energy generation, and I've been working on the development of various what we would call thermomechanical energy storage systems for some years now. My talk, I have to confess, my talk here is one that was prepared for a different conference, and so I've started with a comparison between two types of energy storage. I'm obviously going to, for the purpose of this webinar, focus more on the ammonia-based system, but I need to start with the carbon dioxide system to put things into perspective. Sorry, having a little problem with the technology here. So this picture here is a picture of a relatively advanced in terms of commercialization energy storage system based on liquefaction of carbon dioxide. So I should say there are a diverse range of different technologies being used for energy storage, but the thermomechanical systems, which I'll say a little bit more about in a moment, are really aimed at what we would call medium duration storage. So these are storage events that might cover wind lulls, for example, that could last up to several days. So at the top of my slide here, I've mentioned CGES, which is compressed gas energy storage, which comprises mainly compressed air energy storage, but there's a focus now on compressing other types of gas. And LGES is liquefied gas energy storage. So the energy dome system, which is shown here, being developed in Italy, consists of liquefying carbon dioxide. Now, this has some advantages in terms of having a relatively high energy density, But one has to reckon with, if you're trying to either liquefy or compress any gas as a form of energy storage, you have to reckon with what you're going to do with that gas when it's in its uncompressed state. And so the large sausage-shaped entity on the right-hand side is like an inflatable tent. So it's a very low-tech, simple solution. But it has a high footprint, and there's a considerable cost associated with that. So I've been interested in finding ways of trying to deal with the problem of storing the low pressure gas. In particular, we're interested in making the footprint of these systems sufficiently small that they can be applied to offshore locations where much of the wind energy generation is taking place. And we're targeting, as I've mentioned before, medium duration energy storage. And so to be specific, that's going to be of the order of tens of hours. When one looks at energy storage applications for storing electricity in particular, one can really divide them into short-term things which are managed by batteries, medium-term, which might include these multi-day wind lulls, and then the much longer duration energy storage, which needs to deal with interseasonal variations and indeed inter-year variations. There are significant variations in the production of energy from year to year by wind turbines. The amount of storage that we might need in order to move towards a fully decarbonized grid can be the equivalent of several days of total output from the grid. And if one looks at the cost of the storage, it adds very significantly to the total cost of generation of electricity. So whereas one often talks about the low cost of wind energy generation, by the time you've factored in what's needed to make dispatchable power, the additional costs can be quite significant. So the name of the game here is to look for storage technologies that can really reduce the cost per kilowatt hour of capacity of storage. So to put things into perspective, batteries currently sit at probably several $100 per kilowatt hour. So this was, as I say, I wanted to compare the carbon dioxide and ammonia. I will get onto the ammonia in a moment. The idea here is we have a liquefaction plant, and then rather than putting our low pressure carbon dioxide in the discharge state just into a large inflatable dome, we store it by absorption into some adsorbing medium. One of the best turns out to be zeolite. But even when we do this, we find that we can reduce the footprint of the storage facility enormously, because the volume of that stored low pressure carbon dioxide on the surface of zeolites is a factor of 50 smaller than just storing it as low pressure gas. But there are some difficulties associated with this, in that getting the sort of thermal matching between the liquefaction process and the adsorption process to match each other really requires a heat input. The other thing is that this really turns out to be too expensive, and the reason for that is that you need probably about 25 kilograms of zeolite per kilowatt hour capacity of storage, and even with the most optimistic estimates for the cost of zeolite, that adds significantly to the cost. Just quickly to go into a little bit of detail of the plant that's required to do this. The liquefaction plant comprises a series of compressions and then heat transfers and so on. What we're really exploiting here, if I just move back to the previous slide to make this clearer, the process of liquefaction, as I say, it has these compressions. The gas gets hot, we transfer the heat and use that heat to drive the endothermic desorption process. Having ascertained that the cost was really a little bit too high for the CO2 system, we were looking into, with my colleagues in both chemical engineering and mechanical engineering in the University of Cambridge, looking into other possibilities. And so ammonia came up as really an excellent candidate for a storage facility. So again, if I just emphasize the difference with Laura's presentation, where really she's thinking about using effectively using ammonia as a fuel, so a synthetic fuel, which is very useful for long-term storage. The focus here is on medium duration, and we're not consuming the ammonia, we're just using it as a storage medium. So one of the very useful features about ammonia in this context is its very high solubility in water. So in contrast to the CO2 system, where you would adsorb on the surface of an adsorbent, here we're absorbing in the water. So the tank on the top left-hand side is a kind of saturated solution of ammonia, what I think Rosa will later be referring to as aqua-ammonia. And our system comprises a separation plant, the details of which I won't go into here. We're trying to find ways of making that separation process as close to thermodynamically reversible, which again is a very important aspect for all of these storage technologies. By striving to obtain reversibility, we get much better round-trip efficiencies. So similar to the CO2 system, we have a liquefaction plant. That's going to involve compression processes and so on. And we transfer that heat from that and use that to drive the separation process. And then we store as liquid ammonia in tank 3 on the right-hand side. The point to note about this is that all of these tanks are effectively, again, using the sort of unique features of ammonia here. All of these tanks can be at ambient pressure. Only the liquid ammonia tank is cold, so it needs some insulation for long duration storage. And in contrast to the CO2 system, because we're storing our low pressure ammonia by absorption in water, we can easily move that solution around. We can pump it, we can pass it through heat exchangers and so on. So that gives us a lot of flexibility in plant design. So I mentioned before that the CO2 system had some difficulties associated with it, and one of those was the fact that the process really needs an additional heat input in order to obtain a reasonable round-trip efficiency. So it's interesting to speculate as to why that is the case. It's in order to ascertain whether a system is going to need a heat input or not, we can calculate a thing called the maximum adiabatic charge efficiency, and we can do this without needing to know the precise details of all of the liquefaction and separation plant. We just draw a box, the control volume, the dotted line shown there around all of our plant, and we look at the conditions of storage. And once we've specified those conditions of storage, and as I say, we would want those tanks to be at ambient pressure, so that really essentially fixes all those conditions, we can work out the enthalpy and entropy changes associated with the processes and calculate what would then be the maximum charge efficiency, which is defined in terms of the exergy change, i.e. the change in capacity for undertaking useful work, divided through by the actual work input. Now, our actual process may not be adiabatic, so this really just, by measuring this or by calculating this this quantity, the MACE, we have a way of establishing whether our system is going to be able to operate in isolation without a heat input. So very briefly, as I'm conscious of the time here, I compare on the left-hand side the best we can possibly do with the carbon dioxide system. So the best adiabatic charge efficiency that can be achieved there is around about 55%. So one has to bear in mind that the round-trip efficiency is the product of the charge efficiency, the self-discharge efficiency, and then the discharge efficiency. And so if your charge efficiency is only about 55%, your round-trip efficiency is going to be very low. and that really tells us that the CO2 system really needs a heat input to be able to ascertain, or rather attain, a reasonable round trip efficiency. We've got much more flexibility with the ammonia system, and simply by tuning the temperatures and so on, it looks like we can get a system that will be independent of heat requirements. I'm just going to finish off here by summarizing some of the main features. Again, these are things we can look at without necessarily going into too much detail of the plant itself. So I've got 3 columns here: the energy dome system, which I showed at the beginning, CO2 system based on absorption within a zeolite, and the ammonia system based on absorption within water and liquefaction. And the table shows some of the key features. So because the energy dome system involved storing liquid ammonia at ambient temperature, the relevant pressure there is around about 65 bar, which makes the storage process quite expensive. You have to pay for those pressure vessels. Carbon dioxide, what we do is we cool the carbon dioxide, so we cool it down to close to its triple point, at which the pressure is about 6 bar, so that reduces that storage cost considerably. But with ammonia, we can do even better. You can store liquid ammonia at 1 bar, slightly lower energy density. So you see the figures there: 66 kilowatt hours per meter cube for ammonia, 76 for carbon dioxide. But the reduction in cost more than compensates for that. It's worth noting that energy is also stored in the essentially chemical energy in moving between the concentrated ammonia solution to the weak ammonia solution. So there's an additional storage there within those solution tanks, which equates to about 15 kilowatts per meter cubed. So just to put that into perspective, if I heat water from ambient to 100 degrees C, I get about 9 kilowatt hours per meter cubed. So 15 is considerably better. And well, round trip efficiencies, the energy dome system does do very well. The CO2 system less well. Our NH3 system to be confirmed. There will be some challenges in there, but these are perhaps worth pursuing given the benefits in terms of the reduced cost. So there's some estimates of the raw energy capacity costs here. So I should stress that these are the costs per unit capacity of storage. They're not per unit of energy delivered. So I'll just finish off with some conclusions here. So I guess it's a rather specific one, but to be able to operate in isolation without needing a heat source gives you a much more independence, allows us to operate a storage system in, for example, offshore locations. The fact that we're dealing with a liquid absorbent gives us much better flexibility. And the storage conditions at ambient pressure, again, add to the potential to reduce costs. And really, as I say, I can't stress enough that if we're going to try and decarbonize totally the electricity system, the demands for storage are really very substantial indeed. So getting down those per kilowatt hour capacity costs are very important. Okay, nonetheless, there's the red points here. There are going to be some challenges in taking this system forward. It may or may not work. In the end, what it has to be able to do is do much better than battery systems, and that's a moving target. Battery prices are coming down, but they're still a long way off from being able to deal with these long duration or medium duration events required for storage. So with that, I will finish my presentation and happy to try and answer questions.
Thank you so much, Alex. That was a very fantastic talk. And we have a couple of minutes here for any potential question, any comments, observation. You could still have a chance to put your questions in the chat, and hopefully Alex would stay with us in a couple of minutes. to answer those?
Yes, I'll be here. I'll be here for another 15 minutes or so. Yeah.
Okay, thank you so much, Alex, for your help here. So far we have covered production of ammonia. So we have green ammonia production. We have covered how we store ammonia. And now we have to think about how we are going to transport ammonia cost effectively. This is what I'm going to have a touch on it. I'm going to introduce the concept of aqua-ammonia to those who might not be familiar with, and also the progress we have made since we have started the aqua-ammonia concept. So let's start. This is the net zero week. So you have heard a lot about net zero targets that we have by 2030, by 2050. And so I'm not going to bore you with all of those, mentioning all of those. So the thing that we know is that we are in an urgent need for finding an alternative, an ultimate, better to say, alternative to natural gas. It is not like that we don't have any available alternatives. For space heating, we do have heat pumps, we have electric heating that you could categorize them both together. But the problem with heat pumps and electric heating is that it cannot be an ultimate solution. If you want to shift toward using electricity for a heating purpose, you will require a huge upfront cost to upgrade the grid. It strains the grid and it cannot handle it. Hydrogen was also a choice for space heating. However, it does have its significant storage and transportation challenges. And also, we came to the point that hydrogen is not suitable enough for residential application, if you want to think about it as space heating, but still does have its potential for power generation. As another alternative, we have ammonia that we always have a problem with its toxicity and corrosiveness. So we started a concept here at the University of Nottingham that is called safe ammonia or aqua-ammonia. What it is formed by dissolving ammonia in water, and it shares all benefits that ammonia have while it minimizes its drawbacks. And what are those two drawbacks is toxicity and corrosiveness. So because we're talking about a dilute ammonia, it is less toxic and it is less corrosive. The most important attribute here is that it is liquid at ambient condition. And at ambient condition, it does have higher volumetric energy density than natural gas, than pure ammonia, and then hydrogen. It is transportable through pipelines. This is a very advantageous point if you want to consider, and it is very easy to store and cheap to store because you could ship it in cheap tanks above ground near ambient pressure. If I want to give you context about the volumetric energy density of aqua-ammonia at different concentration, you have 10%, 20, 25%, and 30%, and the maximum concentration of 47% that you cannot go beyond that. Still, if you just take a look at the vertical axis, we are way above the natural gas and hydrogen at 150 bar, and this is at ambient condition. So we have a liquid at ambient condition that's way more energy dense than natural gas and hydrogen gas. At 30%, let's say 30% of concentration of aqua-ammonia is stable at ambient condition. The whole idea with aqua-ammonia is quite simple. We prepare aqua-ammonia and then we transport it through pipelines. This could be natural gas, current natural gas pipeline. It could be dedicated pipeline because it does have a very simple pipeline, very similar to water network. So we prepare the aqua-ammonia, we transport it through pipeline until it gets to the target points. Upon arrival to the target points, we separate ammonia from water. We have pure ammonia that's going to be used for any application that is currently reliant on natural gas. So it could be used as a fuel for space heating, power generation, or anything. And we have pure distilled water that could be repurposed, recycled, or safely even drained. we did know at the first, when the idea conceived, that the feasibility of aqua-ammonia concept fundamentally depends on the ability to separate ammonia in an energy efficient and economically viable manner. So we started this research at the initial step, and we came to the point that we can separate ammonia from water very cost effectively and very energy efficiently, and by leaving just 17 ppm of ammonia residue in water. And this amount of ammonia residue is way below the standards for safe discharging. What we have done since early 23 that the concept formed here at the University of Nottingham, we secured some funding. We did we made a demonstrator for separation unit. We had some publication. We had lots of great industries on board with us. And we started designing different architecture of systems using aqua-ammonia, like aqua-ammonia in power generation, boilers, in district heating, aqua-ammonia heat pumps, and aqua-ammonia in maritime sector. I give you a very brief introduction of each of these architecture of using aqua-ammonia here, but feel free to scan these QR codes to go to any detail that you want, because it leads you to a paper that we have published for each of those applications. So the first application is using aqua-ammonia for space heating. The idea is quite simple. We prepare aqua-ammonia, transport it through pipeline to the end users. That could be residential units or industrial units. Aqua-ammonia feeds a boiler that is an aqua-ammonia powered boiler, and it is very similar to natural gas boiler in size. It does have a separation unit integrated that's separate ammonia from water and burns the ammonia for hot water and space heating application. The transmission line would be 1/3 of water network. So if repurposing natural gas network for transporting aqua-ammonia is not an option, that could be an option, because we have been doing research on that. If it's once is dedicated transportation line, the size of the transportation line for aqua-ammonia is just 1/3 of water network, and as simple as water network. And for space heating, if we want to cover the whole space heating demand of the UK, we just need 13%, 13% of aqua-ammonia to cover the demand of space heating. And this 1-3% is comparable to home cleaners, so it is quite safe. The boiler is does have a high thermal efficiency, around 95 to 97%, and almost the same size as gas boiler. So another application and system configuration for aqua-ammonia is power generation. So you could prepare aqua-ammonia, transport it through pipeline to the steam power plants. Here again, you have some more details if you want in this QR code that how efficient would the system be. So you are sending fuel and water in one pipeline for power generation. That is a very good attribute because you need lots of water in power generation units. And so you are transferring these two in a single unit, in a single pipeline. Aqua-ammonia power plants can achieve a gross thermal efficiency of 41% and a net efficiency of 35%. And these two exceeds comparable natural gas steam plants. It is safer and simpler to transport, and reuse of existing gas infrastructure, like I mentioned before, is still a case for sending aqua-ammonia. Another application is water and fuel delivery through a single pipeline that could be very useful, especially in water-scarce countries, that you deliver them through one pipeline. And to give you context about that, here you have an energy ratio figure that compares the amount of energy that the current gas network could deliver. So this dash line is 1, so it is the amount of energy that the current gas network would deliver. If you want to use aqua-ammonia of different concentration here within the gas pipeline, the amount of energy ratio shows you how more energy that aqua-ammonia could transfer through the same capacity. So with 6% of aqua-ammonia, you deliver exactly the same amount of energy that natural gas delivers. With 13% that we need for space heating, you're delivering actually 2 or 3 times more than the amount that natural gas would deliver. So, so far we had talked about the different configuration of the aqua-ammonia, and now we're going to how we're going to transport through pipeline this aqua-ammonia and how we're dealing with. The best thing that I want to start with here is that we're going to revisit the widely accepted assumption that dedicated hydrogen pipeline are the best and most economic solution for large-scale renewable energy transmission. Is that really true? Is that, I mean, does hydrogen have to remain in molecular hydrogen form during storage and transmission to be used at end use? We're going to assess that and come to a conclusion here. So the work we did was comparing hydrogen pathway by having hydrogen produced out of the electrolyzers. And if we want to deliver it as a hydrogen, we have to compress it and store it somewhere like a salt cavern, and then transmit it through the pipelines and then use it. This is the first pathway that we call it hydrogen pathway. But we are proposing 2 aqua-ammonia scenarios here. If the end user says that I definitely want hydrogen, what we do is that the hydrogen out of the electrolyzers goes through any process to be synthesized to NH3, to ammonia, and then we mix it with water and we store it in a very cheap above ground ambient condition aqua-ammonia tanks, and then we transmit it through pipeline. At the end, we crack it to hydrogen because the end user needs hydrogen for any reason, and then that's it. The scenario 2 of aqua-ammonia pathway considers that the end user needs the energy, not the hydrogen itself. So again, we get hydrogen out of the electrolyzers, we synthesize it to ammonia, mix it with water, store it in above ground, cheap above ground aqua-ammonia storage, transmit it safely through pipeline, and then separate ammonia from water and use the ammonia itself. We have compared these 3 cases together to see how they work actually together. It's been frozen. So the economic indicator for this comparison is levelized cost of delivery. So we calculate level of cost of delivery for all these 3 pathways, and we introduce a cost ratio that compares those 2 scenarios of aqua-ammonia to hydrogen cost to see how it works. Here is the result. It is quite simple and informative. If you take a look at the cost ratio, because it is the ratio, any number above 1 means that the aqua-ammonia pathway is more expensive than hydrogen, and any number below 1 says that aqua-ammonia pathway is cheaper than hydrogen. For the second scenario that the end user uses NH3 ammonia, we always consistently have the lower cost, and not just a small lower cost. The cost of transportation of aqua-ammonia would be about 20 to 40% of the cost of transportation of hydrogen. And if we want to do the reconversions steps to use hydrogen as an end user through aqua-ammonia, for, like you can see, for the most of the cases, you still have the cost ratios below hydrogen. And this gives a very good information here about how we have to transport energy. So far, we have looked at how energy can be transported over long distances, comparing hydrogen with aqua-ammonia as energy carriers, but transporting the energy is only part of this challenge. So when we transport energy, we have different kind of end users. It could be space heating, industrial or residential. It could be power generation. I tried to cover all of these here. And another end user that we might have is the ports. The ports that have to do the bunkering for the vessels that are going to be net zero also. So here, as the maritime industry moves towards net zero, one of the biggest questions is what fuel will power the ships of the future? And actually, the truth is we don't have a single clear winner yet. There are several promising options, including hydrogen, ammonia, methanol, but each comes with its own challenges. Here we want to assess all of these fuels, and if we want to have any of these fuels in future as an option for vessels, how we have to handle the port side. To investigate this, we had two different categories actually. One for, then you can see on the left side, if you see my cursor here, the left-hand side is hydrogen bunkering pathways that does the, let's say, do the bunkering and feed the hydrogen-powered vessels. So you have four options to do that. You could store hydrogen in compressed gas or liquid form in the port to feed and bunker those hydrogen vessels, or you could use NH3 in liquid form to do that, and then just crack it back to hydrogen. You could use aqua-ammonia in a cheap tanks in the ports, and then separate ammonia from water and crack it to feed the hydrogen tanks. So these are the four options that we have for different scenarios that we have to bunker the vessels, hydrogen-fueled vessels. But for ammonia-fueled vessels, we have two options here. One, to store liquid hydrogen at the ports and bunker the hydrogen-fueled vessels, and the other option to store aqua-ammonia in the tanks at the port, and again, separate aqua-ammonia from water and do the bunkering. The last case is methanol. That is here just as a benchmark to compare the results with. The economic indicator here is levelized cost of bunkered energy that we kind of introduce it and define it as the cost of fuel. We are assuming that we have the fuel at the port with the cost that is announced everywhere. You could have access to the fuel cost. And then we have the capital cost of the devices and components that I showed you in the previous slide. We have maintenance cost and the cost of electricity for pumping, compression, and for those tanks that we are doing in refrigerated, we have electricity for refrigeration as well. That's all. And then we have a delivered energy that is what we are just normalizing the whole cost toward. So all of these scenarios are delivering the same energy. Here is what you can see on the comparison that shows you the overall cost of delivering energy through each bunkering pathway. The first thing we can notice here is the ranking hardly changes as the terminal gets larger. So we have three different terminals here. Regional terminals, that's around 70 megawatt. We have commercial terminals and international terminals. So when you scale up, the cost would not change that much. And direct ammonia bunkering that you can see here remains the lowest cost option. It means that you store ammonia in liquid form and bunker ammonia vessels. But on the hydrogen side, if you could see all of the options that would bunker the hydrogen vessels, all of them are almost the same cost. But still, I want to touch on this aqua-ammonia shortly in future, because it still does have a very good advantage that none of these systems would have, and I'm going to discuss this further. So here, so far we have compared all of those different bunkering pathways individually and identified which ones are the most economical. But in reality, ports face a much bigger challenge than simply choosing the cheapest option. Today, we do not know whether hydrogen, ammonia, or methanol will become the dominant marine fuel in future. And whatever we decide now will remain in place for about 30 or 50 years. So basically, the conventional approach would be to build separate infrastructure that could handle hydrogen and ammonia, but that means separate storage systems, separate handling facilities, and ultimately higher investments with the risk that one of those systems may become underutilized if the market develops differently than expected. The aqua-ammonia concept offers a different strategy here. Instead of investing two independent storage infrastructure that you could see in the left picture here, the port can invest in a single atmospheric aqua-ammonia storage system. From that same storage, the operator can either recover ammonia for ammonia-fueled vessels or hydrogen for hydrogen-fueled vessels. So depending on the demand, with one single infrastructure, we could bunker both ammonia and hydrogen vessel fuels. So the real value of aqua-ammonia is not simply whether it has the lowest cost or not. Its main advantage is providing infrastructure flexibility, and it allows the ports to adapt to future fuel demands while reducing the risk of any asset being unused, actually. But here you might ask, so why would we need at all aqua-ammonia to have flexibility? Somebody might ask me, you said that storing ammonia, liquid ammonia at port is the kind of, let's say, cheapest option. How come we are not using ammonia in the ports and then feed both hydrogen vessels and hydrogen powered vessels and ammonia powered vessel by cracking it? So this could be an option. I want to say, if you go back to my first talk that we transported aqua-ammonia through pipeline, you could see that this option that you store aqua-ammonia in the port does have another advantage, because it gets aqua-ammonia through the pipeline, from the pipeline, while this NH3 storage at the port do not have such an option at all. So with about 10% higher cost, we are achieving both the flexibility and also both the transportation, so the fuel supply would be much easier. I want to wrap it up here. The key takeaways from my talk is, for long distance energy transmission, aqua-ammonia provides a lower cost alternative to transporting hydrogen. And by combining, and this is because of combining low pressure pipeline transport, very simple and cheap, and inexpensive atmospheric storage. At ports, although we know that direct ammonia bunkering remains the lowest option, but still aqua-ammonia provides a single storage platform capable of supplying both ammonia and hydrogen-fueled vessels that has fed from a pipeline, from a transmission line. And the true value of aqua-ammonia lies in enabling the integrated, flexible, and future-proof zero carbon energy. So what I want to emphasize here is that aqua-ammonia is not competing at all with hydrogen or ammonia as a fuel. Aqua-ammonia tries to enable their practical deployment. So we have hydrogen, we can combust hydrogen, but the problem with hydrogen is that we cannot transport it cheaply. So aqua-ammonia makes it feasible and cost-effective. Thank you very much for your attention here. If there is any question, please just drop it in the chat. And here is my emails, and also one of my colleagues' emails that we will be responsive if you have any question after that. So, any question here? If not, I'm going to hand it over to Sayed. So let me give you a brief introduction from Dr. Sayed Mashrouk. Is a lecturer in thermal and combustion science at Cardiff University and the Zero Carbon Fuels theme lead at the Net Zero Innovation Institute. His research focuses on ammonia and hydrogen combustion, low emission power generation, and advanced combustion technologies for industrial, marine, and aerospace application. He has played a leading role in the development of innovative ammonia combustion system, including Cardiff's world first demonstration of a 100% fired boiler using an integrated cracking burner. We are so thrilled to hear about you, Sayed, and I hand it over to you. Thank you.
Thanks, Rosa. Thanks, everyone. So today I'm going to talk about this project that has been recently concluded that we led from Cardiff University. This project's name is MBurn. Let me just get my point. Yeah, MBurn project. It's been funded by DESNES. We had a £3.5 million funding. Our industrial partner was Flowgas, and it was managed by ERM, the project. When I talk about this MBurn project, so we went from 10 kilowatt to 1 megawatt in less than 3 years in this project. That's the focus. I want to have this in your mind when I deliver this presentation. So I'm not going to go through this at all. Laura covered it extensively, so I'm going to go ahead. In here as well, Laura covered. Just one thing I want to show you here. If you look at this bottom right graph here, what is the levelized cost are here? So you have ammonia costing, liquid hydrogen costing, and liquid organic hydrogen carrier costing at port. You can see that if you look at the final figures, both ammonia and LOHC has similar sort of cost, where the cheapest one is liquid hydrogen. But when they did this costing, so what they presume that we're gonna crack all of this ammonia and then make hydrogen and then combust it. But if I take this out, if I take this out, this cracking portion here, ammonia becomes very viable and very attractive solutions. So Laura covered this as well, how we're going to produce ammonia. So I'm going to move on. So with the ammonia, we have 4 main challenges. The first one is the carbon-free synthesis. We talked about, Laura talked about quite a bit on that. And then the next one is the power generation. That's where this presentation comes in. So at a utility scale, so which this project has delivered up to 1.4 megawatt with stable and low emissions. And there is obviously the third point is the public acceptance through safe regulations and appropriate community engagement. So for this study, when you go from 10 kilowatt to 1 megawatt or up to 1.4 megawatt, actually, we have gone through a rigorous safety regulations. We have gone through HAZOP, HAZIT, through DNV. So I'm going to talk about a bit about those as I go on. And about the public acceptance. So a few years back in Cardiff, we had a PhD student who looked at public acceptance in the UK and in the Mexico, how public thinks about having ammonia as a fuel, everyday fuel. So if you have interest on that, if you contact me, I can forward you her details and her PhD thesis as well if you want to look a bit more on the public acceptance side of things. And finally, it has to make money, right? Anything, whatever solutions we have, it has to make money for the world to go ahead. So on the MBurn one, the first stage was to go from 10 kilowatt to half a megawatt, and that happened at Cardiff University School of Engineering. And you can imagine, so to having this half a ton liquid ammonia on campus with thousands of students, staff members, we had to go through rigorous health and safety studies before we were even allowed to do that. So the way this works, so we had liquid ammonia being withdrawn from this tank, and we had a vaporizer that's been made by our industrial partner, Flowgas, which vaporized this liquid ammonia to gaseous, and then it fed to this combustion chamber here. So we also had Flowgas LPG cylinders. So we started with propane, then we converted to full ammonia. Right, but what you cannot see here, there is no hydrogen cylinder in these slides, because we had hydrogen cylinder before, and because we had this small incident with the hydrogen. And then the health and safety study came out that we cannot have any hydrogen on site at this scale of testing because of the volatility with the hydrogen combustion. And the same conclusion was made when we went to DNV for stage 2 experiments as well. So just to give you a quick setup, so we had a dedicated air fan with the premixing chamber. We started with propane a gaseous flow. We had a flame on. And then we put some liquid ammonia to the vaporizer, have gaseous ammonia, again controlled it, and now we have a propane ammonia flame. And then what we did then for the secondary stage, we put some air through there. So the way we do it, we burn it a bit rich with ammonia so that NOx goes down considerably. And then because you're burning rich, when I say rich, I mean that I'm not giving enough air to burn it completely, right? So that means there is some ammonia is left over that's not burned. So this secondary air injection here burns the rest of them. And then finally, what was very innovative about this project, we had designed the ammonia cracker that was in situ in the flame, and that was using the waste heat from the flame and delivering nitrogen, hydrogen, ammonia mixture to the premixing chamber as well. So finally, what we did, we completely take out propane completely out, and then we had actually self-sustaining complete pure ammonia with hydrogen coming from the cracker. For the emissions, we had QCl emission QCl analyzer, which could measure NO, NO2, N2O, ammonia, CO, CO2, O2, and water. And we had Agilent and Emerson Extreme for the hydrogen measurements. And for the optically, we have a LaVision high-speed camera that we have used for OH, NH, NH2 star collection, and a Nikon camera, DSLR camera for ultraviolet images. So what you're seeing here, there is 4 videos here. On the first video, we have 70-30 ammonia propane, and then 80-20, then 85-15, and finally 90-10. What we can see very considerably here, there's a blue tinge that comes from the fossil fuel at 70-30. But as I'm driving towards more and more ammonia, you can barely see any blue tinge here. But what is very important to see here, the stability of the flame. Flame is very stable. Even at 90% ammonia, my flame was very, very stable. So then this is a video of the when the experiment was taken. So we have air coming through here. The patented burner, the design in Cardiff, is somewhere here. And you can see some flame here. Obviously, the flame was so bright. This is 0.5 megawatt flame here. Flame was so bright, my camera couldn't capture properly. We had this, so this thing, we call it Thomas, this rig. It is rated up to 1.6 megawatt. We also made a window at the back end to see the flame from the back end as well. So moving on the emissions part of thing. So we have NO here. So I have 2 solid lines here. So one is this purple line, one is this red line. So purple line is the limit. If you're making a new burner, new boiler, that's the limit of NO. That's current regulation. And the red one is the limit if you are retrofitting and making retrofitting to an existing boiler with new combustion system. So, and this is the data that we have collected at stage 1. So you can see, obviously I drive it so that I can see my stability range, but we can produce a stable flame with NO very close and even below the requirement by the regulator. And this is for the ammonia. Obviously, ammonia gonna go higher if I have my global equivalence ratio is more than 1. That means I'm not giving it enough air to burn it completely. And we had negligible N2O, NO2, and hydrogen. When you talk about N2O, you might know the N2O is 300 times more global warming potential than CO2, but we didn't measure any N2O whatsoever in here. And then for the CO, again, CO was a bit high when you go rich, globally rich. That means we're not giving enough air to combust properly. But you can see that these blue ones, where it was 20% cracked, that means there was no carbon present in there. There's no CO in there either, even when you went rich. And finally, which is the most important emissions here. So you can see with the 100% propane, that was my CO2 emissions. And then when I had 91% ammonia in there, I already reduced my CO2 emissions by about 70%. And then 95% ammonia, I reduce nearly 80%. And when I go from fully cracked using my integrated cracking system, I've gone for 100% possible decarbonization in there. And then I go for, then we finish this stage 1 experiment. Then we move on to DNV in Spade Adam in Brampton, UK, up in Carlisle, where we have conducted this stage 2 of the experiment, where we actually purchased a boiler, a brand new boiler that can go up to 3 megawatt. We retrofitted the whole system. I'll talk about this a bit here now. So this is our, this was our test site. So this is where the boiler was situated. We had 2 flow gas LPG there, and this was a 1 ISO tank, that means 12 tons of ammonia in there, and liquids being withdrawn. And similar to stage 1 site, we had a vaporizer that was collecting the ammonia and vaporizing and feeding it through our system. And here is the control systems. We were all situated over here, and we had the our electrical systems over there as well. And by there here, you can see this is where the air fan was situated. The air was supplied from here. Now, safety system, again, this we have gone through nearly 1 year of safety study before we conducted this test. You can see the amount of safety features we put down here, this amount of work that we've gone through. But again, DNV did not allow us to have hydrogen of that magnitude on site. So that's why it became a bit more complicated, because we had to make it's more because no hydrogen is there. We could not supply any pure hydrogen through the compressed hydrogen gases. So we had to make it more robust for the ammonia cases, right? For the cracker thing going on. So it has to be, it has to be more safety featured in there. And finally, this is, you can see the flame here. This flame is very orange. So that means it's mostly ammonia there. And what we can see here, we are producing steam. That means under load, I'm burning now ammonia and producing steam. So this video was taken from the control system, from the control room, sorry. So we had a what do you call it, a endoscope that was at the back of the boiler. So you could see the live pictures, live videos when we were testing for monitoring. And here again, you can see when you go to nearly 1.4 megawatt with 85% ammonia present, and the flame, you can see this lovely flame looking very, very stable. Moving on again, so I have some more. So the first row here is all 1 megawatt with different ammonia concentration. So from 75% ammonia to 90% ammonia. They can see the blue tinge here, and the blue tinge keep going away as I'm putting more and more ammonia in there. And then finally in here, I tried to make very high ammonia cases. Obviously, I was limited by my MFC that was controlling, not the MFC, it's the control valve that was controlling it. So I slightly reduced my my power as I go more and more in ammonia. But again, you can see the flame was very, very stable, and that this line that you see here is actually the igniter that ignited the flame. Finally, some emissions to compare between the stage 1 and stage 2 experiment. What you see here, this triangle is the furnace, that means stage 1 experiment. And the circle here, again, furnace up to 91% ammonia. And the blue one is the boiler that up 91% ammonia. So what you can see here with the NO actually improved somewhat with the boiler. And the reason behind that, because my flame was under load, my flame was cold, right? My flame was cold, so NO was a bit reduced from that sense, because you're having less thermal NO in there. But as a downside, my ammonia increased, right? But then again, with more study going on here to work on it in more detail. So we are looking for future funding to go and work on it more. We are working with Rosa actually to get some future funding on this, to combine this aqua-ammonia and this boiler at the same condition. Again, I put these 2 lines where I have the purple one is the limit for a new boiler, and the red one is the NO limit for a retrofitted boiler. You can see that we are very close, and even we were below that limit, which is great. again, similar graph here, but what I want to show you here is this thing here. So we have comparison in literature from 5 kilowatt to literature, we have up to only 50 kilowatt of data. So in this study, we did it to 1.4 megawatt, but unfortunately on the last day, our gas analyzer wasn't working. The heating line broke down under the heat. So we only had data for the 500 kilowatt, but you can see the comparison. So we are actually, emissions-wise, a very, really nice place situated. And this is some drone shot while we were testing. So this here is the exhaust gases that's coming out, and this here is the steam that's being produced. Okay. Finally, this is again a nice video of the steam being produced. So we have just showed with this demonstration that ammonia can be used for power purposes via combustion. And obviously, we are looking for future funding to go more into this thing and make it more so. This system that you've designed and demonstrated, it needs at least 1 or 2 years more of iteration to be consumer ready, to be self-autonomous, and that's still looking for the future funding. We are trying many different avenues, and if you want to collaborate with us or be a partner in this, so feel free to talk to me, send me an email. We are always welcoming collaboration. And finally, this is my team. This is the picture that we have taken on the first day of stage 1 testing in Cardiff. It's led by Agustin and myself. We have several postdocs and PhD students in our lab. With that, I think I'm just in time, Rosa.
Yes, Sayed, you were, and actually I myself was not in time. Thank you so much. Thanks for your great presentation. So any question here for Sayed? So still you have a chance to email your questions if you have any. It is 10:30, and before we close, I would like to thank all of our speakers for their excellent presentation and for sharing their research today. So this is something that I suppose you could just handle it through the chat, Sayed. So today's discussion have shown that ammonia is much more than an alternative fuel. It is becoming an important part of future low carbon energy landscape. We have explored its role in production, utilization, combustion, and maritime application. Sorry, I got distracted by this. And while also highlighting emerging concepts like aqua-ammonia and how aqua-ammonia could facilitate use of ammonia, transportation of ammonia, and also hydrogen. What is actually encouraging is that progress is being made across academia. The thing that we need is some collaboration between the academic and policymakers and industry sectors. These sectors will be essential. We know that if we want to translate today's research into practical energy solution for future. Finally, I would like to thank you. Thanks everyone who joined us today. We hope this webinar has provided new insights and sparked maybe new ideas and collaborations. We look forward to continuing this conversation in future. And thank you all for your time. And I wish you a wonderful rest of the day.
Thanks, Rosa.
Thanks. Bye.
Bye-bye.